So the second presentation and final presentation for this unit is doing mass calculations using the chemical equation, chemical reactions. So you know in lab, anytime we want to weigh something or measure the quantity of something, we never measure it in moles, we always measure it in grams. We can still use a chemical equation to calculate quantities using mass because we know how to interconvert between mass and moles. We learned that in our last unit. We use the molar mass. We can interconvert mass to moles or moles to mass. So if we know the starting amount of one of the materials in the equation, we balance the equation, then we convert the mass of what we're given into moles of what we're given. We use the balanced equation to find the appropriate mole ratio and convert moles of what we're giving into moles of what we know, of what we want. And then we can finally use the molar mass of what we want to convert back to mass of product. And it sounds like a lot. It's 3 steps. You already know how to do all 3 of them. And I'm going to work through, I think, 3 examples in this PowerPoint, and then there will be additional examples worked on the EduCreations, and we can always do a conference online to work more problems for you. To convert the mass of one component of a chemical reaction into the mass of another, you again follow the logical steps. What do I know? Where am I going? And how can I get there? The how can I get there just got a little longer. So using this pathway of thought, we're going to apply this principle of stoichiometry. And stoichiometry is the process of using a balanced chemical equation to calculate the relative masses of reactants and products involved in a reaction. So we've done kind of stoichiometry light, where we've started with moles and ended up with moles. The full stoichiometry, you start with mass and end up with mass, because typically in lab, that's what we do. So in order to do this, we're going to use the pathway that I'm writing out for you below. In this pathway, we start with the mass of what we know. We're going to convert that into moles of what we know using the molar mass. Then we use our new mole ratio to convert that into moles of what we don't know. And finally, we use the molar mass. So stepped out for you, again, are the 3 steps. What do we know? We know mass of one of the components. So we're going to convert that into moles of that component using the molar mass. Then we want to convert that into moles of what we know, of what we want. So we use that new mole ratio of what we want to what we know. And finally, we'll convert the moles of what we want into the mass of what we want. So that's how we would apply the principles of the balanced chemical equation. So best way to do this really is to just look at a couple of examples. So we're going to start with the following unbalanced chemical equation. And this is chromium solid plus oxygen gas produces chromium 3 oxide solid. So this is a combination, probably also a combustion of the metal chromium. And the problem says, how many grams of chromium 3 oxide can be produced from 15.0 grams of solid chromium and excess oxygen? And remember, excess just means we have more than enough. So the first thing we need to do is ask, what do we know? So far, what we know is we have an unbalanced equation, and we're starting with 15 grams of chromium. And we know from the periodic table the atomic mass of chromium is 52 and the atomic mass of oxygen is 16. Then we can ask ourselves, where are we going? We want to determine the mass of chromium 3 oxide that is produced by the 15 grams of chromium reacted with excess oxygen. And in order to do this, we need to find a couple of things. The first thing we need to do is balance the equation. So we balance the equation. I'm not going to walk you through the balancing, but if you look up here, we start with 2 oxygens and 1 chromium in the reactants, and 2 chromiums and 3 oxygens in the product. And remember, we're going to leave oxygen till the last. So if I balance the chromiums, I can put a 2 in front of chromium. If I then go and try to balance the oxygens, I have a 3 and a 2, so I'm going to put lowest common multiple is 6. Anyway, I'm not going to walk you through the balancing. The balanced equation is 4 chromium solid plus 3 oxygen gas produce 2 chromium 3 oxide solid. And then using the atomic masses of chromium and oxygen, we calculate the molar mass of chromium 3 oxide. I'm also not going to walk you through that calculation. It's 2 times chromium plus 3 times oxygen, and that comes out to 152 grams per mole. So then we have the question, how do we get there? Okay. So remember our steps. The first thing you do is convert mass of what you know into moles of what you know. So in order to do that, we start with the mass of what we know, which is 15.0 grams of chromium, and we multiply it by 1 mole of chromium divided by the molar mass. And they are showing you the crossing out of the units. And with the correct number of significant figures, this comes out to 0.288 moles of chromium. So now we have the first step done. Step 2 of how do we get there, again, there's our balanced equation. In step 2 of how do we get there, we use the mole ratio from the balanced equation to determine the moles of chromium-3 oxide that will be produced. So our mole ratio in this case, if we look up at the numbers, we have 2 moles of chromium-3 oxide produced for every 4 moles of chromium that are consumed. We've already converted our mass of chromium into moles of chromium. So now we have moles of chromium from the previous slide. That's 0.288. And we just multiply by the mole ratio. And remember, the mole ratio comes from the balancing. Whatever you're trying to find always goes in the numerator. Whatever you're converting from goes in the denominator. And that leaves us with so we basically multiply 2, divide by 4. That's basically dividing by 2. And we end up with 0.144 moles of chromium-3 oxide. And if we then do our last step of how do we get there, here's our equation. We have 0.144 moles of chromium-3 oxide. We multiply by the molar mass of chromium-3 oxide. Our moles drop out, and we end up with 21.9 grams of chromium-3 oxide. At the bottom here, we have the whole thing done in one big string. When we see that in one big string, we end up with the exact same answer. To do this problem, you would start by entering 15.0 in the calculator, then say divided by 52, times 2 divided by 4 times 152. And that will give you the same answer. When you do it in one big string, you can just keep going in your calculations. You don't have to hit the enter button. You don't have to write down intermediate values. You don't have to clear the calculator after each calculation. You will get the same answer. If you're not comfortable doing that, do it in the 3 steps and just write down what you get each time. Here's example number 2. In this example, they're giving us a balanced equation. Very nice of them. And we have the compound tin 2 fluoride is added to some dental products to help prevent cavities. Tin 2 fluoride is SnF2. It is prepared according to the following equation. 1 tin solid plus 2 hydrofluoric acid produce 1 tin 2 fluoride aqueous plus hydrogen gas. How many grams of tin 2 fluoride can be produced? How many grams can be produced? So that's what we're trying to find from 55.0 grams of hydrofluoric acid or hydrogen fluoride if there is plenty of tin available to react. So now we have an incorrect name. Hydrogen fluoride should be hydrofluoric acid, but it doesn't matter. The tin is excess, so we don't have to worry about it. So we know hydrogen fluoride, and we're trying to find tin 2 fluoride. So I've rewritten the problem and the equation for you and the question. So again, we're going to start with our 3 questions. What do we know? Where are we going? And how can we get there? So what do we know? We know the mass of hydrogen fluoride or hydrofluoric acid. They tell us in the problem 55.0 grams of HF are reacted. Where are we going? We want to find the mass of tin 2 fluoride. How can we get there? We're going to need 3 things: the molar mass of hydrogen fluoride, the mole ratio between tin 2 fluoride and hydrogen fluoride, and finally the molar mass of tin 2 fluoride. So here again is the equation. Here's the problem. Step 1, convert what you know to moles. So we know hydrogen fluoride, 55.0 grams. We want to convert that into moles of hydrogen fluoride, so we're going to say 1 mole HF divided by the molar mass of HF, which is 20.01 grams of HF per mole. I'm not going through the calculations. It's 1 hydrogen plus 1 fluorine. I'm using hydrogen from the periodic table that is in Canvas. And when you do this math, you get 2.50 moles of hydrogen fluoride are equal to 55.0 grams of hydrogen fluoride. Step 2 of how can I get there? 2.5 moles of HF. Now we're going to multiply by the mole ratio between tin 2 fluoride and HF in the equation. There's 1 mole of tin 2 fluoride for every 2 moles of HF, so our units will cancel. I'm going to cancel my units, which I should have done up here. And that produces 1.25 moles. And finally, the last step, 1.25 moles of tin 2 fluoride, I forgot to subscript that 2, times the molar mass of tin 2 for you. But now we see that the moles on top and the moles on bottom cancel, and we end up with grams of tin 2 fluoride are produced for every 55 grams of HF that react. So on this problem, here is the string. They do it out as one long string. The reason the masses are slightly different is they used a different molar mass for hydrogen. It does not change the answer to the problem. If you recall from the previous slide, we got a number of 215 grams. So did they. We did the problem right. If you want to string it out like this for your calculations, in the calculator you would say 55.0. You don't have to do times 1, but you can if you want to. Divided by 20.008, or in our case it was 20.01, divided by 2 times 156.71. So basically for the calculator, anytime something is in the numerator, you hit times. Anytime something is in the denominator, you're going to use divide. The calculator does what you tell it to do. So if something's in the denominator and you're not putting it in parentheses, just have to keep hitting divide, 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 divide. So you'd say 55.0 divided by 20.008 divided by 2 times 156.71. Try that. You should get the right answer if your calculator works like a calculator is supposed to work. And we have one more example. There will be some examples on EduCreations. Consider the following balanced reaction. PCl3 plus 3H2O yields H3PO3 plus 3HCl. Notice this is a terrible equation. There are no phases. We don't really care. Right now we're just doing stoichiometry, but if you wrote an equation like this, it would be pretty bad. Okay, question says, what mass of water is needed to completely react with 20.0 grams of PCl3? Again, our 3 questions. What do we know? We know the mass of PCl3 is 20.0 grams. We know the balanced chemical equation, and we know how to find molar mass. That's also what we know. Where are we going? We want to know the mass of water that's produced. How can we get there? There's our 3 ways to get there. The molar mass of PCl3 is needed, the mole ratio for water and PCl3 from the equation, and the molar mass of water. And again, I'm using hydrogen mass of 1.01, which is why my masses are slightly different than theirs. Again, it doesn't matter in the answer. Okay. So how can we get there? It's 3 steps. It's 3 conversions back to back to back. So here's my reaction again. Step 1, convert grams of PCl3 into moles of PCl3. How do I do that? I multiply by 1 over the molar mass. So my grams will cancel, and I end up with 0.146 moles PCl3. Now that's rounded. You're going to see that the next number really doesn't make any sense. It doesn't matter. It's because I didn't clear my calculator. In the end, we get to the same answer. So if you rounded it and you get a slightly different number for the next one, that's okay. Step 2, we convert moles of PCl3 to moles of water. If we look at the equation, the mole ratio is 3 moles of water for every 1 mole of PCl3. So that's where we get the numbers in the mole ratio. So we have 0.146 moles, or whatever my calculator said, times 3 divided by 1 gives me on my calculator 0.437, again rounded. And then finally we take that and we multiply the moles of water times the molar mass of water to get 7.87 grams of water. On this slide, they're going to show you the whole thing all strung together. The reason their molar mass of water again is different is because they're using a different mass for hydrogen. In this problem, what did we get? 7.87 grams. When you do this whole thing on the calculator, you would enter 20.0 divided by 137.32 times 3, divided by 1, but you don't have to do that, times 18.016 or 18.02. And the correct answer is 7.87 grams. Okay. That is the end of this presentation. Make sure you watch the EduCreations videos. Make sure that you do some of the problems in the worksheets. If you want additional help, make sure you reach out to schedule some special conference time or tutoring time.